This video is going to cover a summary of aerospace engineering, specifically aeronautics, and what this major entails as well as careers. Like I said in the other video, aerospace can be broken up into aeronautics and astronautics, where aeronautics is about things that fly in the air, and astronautics is about things that go into space. Now, as you can imagine, aeronautical engineers can work on planes, helicopters, missiles, unmanned aircrafts, fighter jets, and so on. But because this discipline is big on aerodynamics, you could see aeronautical engineers working on cars and how to shape them to maximize their fuel efficiency. They can work on boats which interact with air, bullet trains which can go up to 200 miles per hour. I'm sure many of you know of the Hyperloop that's being worked on right now, which would be a mode of transportation that would propel people in a pod-like vehicle through a tube at maximum speeds of almost 800 miles per hour. Well, this needs aerospace engineers as well, because at speeds that high, there's a lot of airflow issues that need to be accounted for in that tube. So make sure when you think of aeronautical engineering to think of the various applications it applies to. And also, like I said in the astronautics video, there are many subfields that you can dive into when it comes to air or spacecrafts where you work on a more specific aspect of the vehicle. Some of the big ones I'll talk about are aerodynamics, propulsion, controls and stability, and structures. So first, aerodynamics is of course where you study the properties of moving air and also its interaction with solid objects. After you go through the basics of fluid mechanics like water moving through a pipe, you get into the actual aerodynamics and you start with subsonic flow, which is airflow that is less than the speed of sound, and the speed of sound is called Mach 1. The planes we ride on, helicopters, and certain types of military aircrafts are all subsonic aircrafts. The planes you go on are typically Mach 0.8 or around 600 miles per hour, while the speed of sound is about 770 miles per hour. So first you'd learn airfoil theory, which is just the theory behind airfoils, their shapes, and how they produce lift. Two big aspects of these you'll analyze are lift and drag. When you have an aircraft, there are four forces acting on it. Thrust, provided by the engine, which is left for propulsions. Lift, which is created due to complex interactions with the air and the wing. Drag, which is basically friction from the air, and the weight of the vehicle due to gravity. So you'd see how those airfoils, like on the left, provide a certain amount of lift and drag based on their shape and on the physics of that fluid flow and interaction. You may be given some random object that's traveling through the air and asked to find the drag on it or the pressure at different points. Also, when it comes to wings, what angle is the best for optimum lift and less drag? At some small arbitrary angle, you see how air splits at the front and then follows the curvature of the wing. This is ideal, but if we increase the angle too much, the flow becomes separated at the back, and that's what we call a stall, where the drag increases and the lift decreases, which obviously is not what you want while on a plane. There's much more to this because if you've been to air shows, you've seen planes that even fly upside down. So just note this is the very basics. Then you move on to supersonic aerodynamics. This is where aircrafts move faster than the speed of sound. These are mostly military aircrafts like fighter jets that are meant for defense purposes. And note, defense is a huge sector for aerospace engineers to get into. So what happens at these speeds? Well, I'm sure many of you know of the Doppler effect, where as a source is moving and emitting noise, the relative frequency increases for objects in front and decreases for ones in back. The sound waves basically are closer to each other in the front and the frequency goes up, which is why a motorcycle sounds different approaching you compared to driving away from you. Now what about at the speed of sound? Well, if we move slower than sound, the waves can be drawn circularly like this and are closer together in the direction of motion, but not on top of each other. Then at the speed of sound, they actually bunch up on top of each other or constructively interfere. This combining of sound waves in front is extremely loud and is known as a sonic boom, which can break glass and shake windows while thousands of feet in the air. Then what about an object traveling faster than sound? Well, then the waves are created but are trailing the aircraft. There is still a sonic boom, but the waves combine constructively at an angle here rather than in front. So they might give you that angle of the shock wave, which is what that's called, and ask you to calculate the Mach number or speed that the aircraft is flying at. The faster the speed, the smaller that angle, and that's something that we can calculate. Now at supersonic speeds, the drag on the aircraft also increases much faster as the aircraft speeds up. To compensate for all this, supersonic aircrafts are made to be more narrow and have a sleeker look to them. Then there's also hypersonic flow, which I'll talk about soon, but this is for aircraft traveling at Mach 5 or higher, which is just under 4,000 miles per hour. To put that in perspective, you could fly from Los Angeles to New York in just under 40 minutes as opposed to 5 hours. In your career, two big things you can do are design or testing. If you did design, you might be developing the aircraft wing on the computer and use computational fluid dynamics, which I've shown before. Then you could simulate how it will respond to interactions with the air. As you saw, designing a supersonic or hypersonic aircraft can be much different than a subsonic one. The higher the speed, the more challenges you face. Or you could do testing using a wind tunnel, for example, where you put the physical structure in a large tunnel and run fast winds through it to see whether it behaves like the computer simulation predicted. In fact, for a lab, one school did parachute testing in a wind tunnel where they tested various parachute shapes to see which was the best. But again, this can apply to cars, bikes, and other vehicles that all need to account for aerodynamics. Now let's move on to propulsion. This is where you obviously learn about the different types of propulsion systems used for an aircraft. The big ones you'll probably learn are the turboprop, turboshaft, turbofan, and turbojet. So here's a picture of a turbojet, and this is basically how it works. Air comes in the front as the aircraft moves. It's compressed or squeezed through many rotating blades which add energy to the fluid, which causes its pressure to rise. Then fuel is added and it's lit on fire in the combustion chamber. Then that travels through a turbine which provides energy back to the compressor. And then the air exits out the back at a fast speed and high temperature to provide the thrust to the aircraft. But if you look at the turboshaft, turbofan, and turboprop, you'll see they look very similar. The overall concept of these isn't much different. I'm sure most of you have seen the propulsion system on an aircraft, at least the outside of it. Well, the things just listed are what's going on the inside. So you'll learn the aerodynamics of the spinning blades in the compressor, which like I said can have a lot of stages to it. You'll analyze the interactions of the fluid as it moves through the various stages. You'll analyze the efficiency of the blades, how do you minimize the amount of blades needed, you'll analyze horsepower, and much more. Again, you may design these on the computer in your career, or you do testing on them to see if all the specifications are met. Those aren't the only jobs, but are two big ones. But what about for supersonic aircrafts? At supersonic speeds that are high enough, the engine doesn't require a compressor or a turbine here for reasons you'll learn about that relate pressure and temperature of the fluid. If you remove those, we have what is called a ramjet. These are best used for aircrafts flying between Mach 3 and 6. Supersonic aircrafts, like I said, experience much more drag at those high speeds, meaning the air is pushing back on the aircraft to slow it down more. Therefore, you need an engine that can supply the right amount of force to compensate for this. Supersonic aircrafts also fly at extremely high altitudes. At those altitudes, the air density is much lower. The engines must be able to compensate for that and intake large amounts of air, because after all, that air is what's making the propulsion work. Then what if you want to get well into hypersonic speeds? Well, in this case you use a scramjet, and we actually don't know the maximum speed that these can go. If maybe you're considering a master's or even a PhD and you want to do research on propulsion systems, this is something you could do. Research on hypersonic engines. One university a while back put a model of a scramjet in a tunnel, then added a hypersonic flow and measured the overall force. They found that the scramjet was able to provide more thrust than the drag it was subject to, meaning this was able to accelerate successfully and overcome drag, which at high speeds is not easy to do, and research is still being done. Theoretically, we predict these can travel somewhere between Mach 12 and Mach 24, but we haven't gotten there yet. So if you want to dive into propulsion research and get us to much faster speeds, this is something to look into. But remember, most jobs will involve designing and testing already known propulsion methods. Now let's go over controls and stability. This is essentially about using inputs, then doing mathematical modeling to produce a stable and desirable output. For example, aircrafts have autopilot on them. The pilot may input a certain heading or direction, and the aircraft control system has to be able to keep the plane headed in that direction. If you enable autopilot, you wouldn't want a really fast and abrupt change because that may cause discomfort. You want a smooth transition to put the aircraft on the right course. All this is about making sure the control system produces stable outputs from the inputs it receives. So one big thing you'll learn is coordinate systems for the aircraft. If an aircraft is moving forward, we may call this the x direction, which is parallel to the ground, and this the y direction, which is the direction of gravity. All this seems pretty convenient. But what if the plane is increasing in altitude? Should we keep everything the same? Or maybe we could label the way it's pointing as x. Not parallel to the ground like before, but it's still convenient here. And then perpendicular to that would be our y. But also, our plane might be going in this direction even though the nose is pointing slightly higher. And this is something important to note. The plane doesn't always go in the direction it's pointing. In fact, you're just looking at a picture right now. For all you know, this plane is falling out of the sky while pointed slightly up. So don't get confused about this. And by the way, the angle between that relative airflow and where the plane is pointing is called the angle of attack. When that angle gets too big, that's when the plane stalls. Remember the picture from before of the separated airflow? As you can see, this would be like the plane moving to the left, then trying to go up by pointing its nose at an angle, which would make that angle of attack too much in this case, and that's why you see that it stalls. Then if that blue line we call our x-axis, then perpendicular to that would be the y-axis, which is also the direction of lift. And perpendicular to that, which would be the negative x direction, is drag. So this is also really convenient, especially for when you have to sum the forces in the x and y direction, which you will do to derive various equations of motion, because lift and drag are already in the right directions. None of the systems are perfect, but they have their advantages. So you'll be doing lots of coordinate system transformations and defining multiple axes for a given aircraft like shown above and more. And hopefully you're also seeing that yes, aerospace engineering is a very math-heavy major. Three of the most fundamental axes you'll learn about are yaw, pitch, and roll. These are the three axes by which an aircraft can be rotated. So as you can see, roll is what happens when an airplane starts turning and it rolls to one side. Pitch would make the plane point more up or down, and yaw would turn the nose side to side. So how does this happen? Well, when a plane turns or rolls, the flaps on the wings move in opposite directions, causing air to push one up and one down, which causes a rolling motion. For yaw, a flap on the back or rudder turns side to side, providing a torque about the plane, allowing it to turn. And for pitch, the two flaps near the rudder are turned in the same direction, which will force the back either down or up, and therefore the nose to go up and down respectively. And thus you have three ways to rotate a plane. And guess what? It's the control systems that have to make sure these changes in direction are handled carefully. You don't want to turn the flaps too much or the plane will roll too far, which would obviously be a huge issue. If the flaps change the pitch too much, that could point the nose too high, which will increase the angle of attack, and that can cause the airplane to stall. The control system keeps these all in check. It's not like you have a rope attached to the flaps where you manually pull for these aircraft you're seeing. There's an entire system that has to work just right. The control system is even used simply to drop those masks you see on planes. The system has an input of pressure from the cabin area and has to open the compartments immediately if pressure has changed too much. We also have unmanned aircraft, so obviously those need really good control systems as there's no direct pilot on the vehicle. One area of research being worked on is flexible wings, as in wings that can morph and change their shape during flight. This is being investigated by NASA as an example to greatly improve flight efficiency and performance. Control systems would be required to change the wings during flight as needed. Now you take very similar controls classes to an electrical engineer because this is a field they can go into as well. So if the controls aspect interests you the most, you could also choose electrical engineering and search for aerospace jobs. You can see in other majors like mechatronics or even computer science, but electrical is a very common one. Now let's move on to structures. This is pretty much the same as it is for astronautical engineers. In fact, you may take the same required courses when it comes to structures. This is all about what you'd imagine, making the structure of the vehicle so that it can withstand all the forces it's subject to. During flight, the wings are subject to a lot of force. There are vibrations that occur, turbulence happens, and the aircraft has to be able to handle all this. The basics of this involves learning about strength, how structures experience fatigue over time, deflection and how something bends when given a certain force, shearing stress, torsion, and all types of forces that a structure can be subject to that I've shown before or what you'll be studying. Although you diverge into specifically aerospace classes, you'll begin just like mechanical and even civil engineers taking all the same classes as them. In your career, you could work on designing the structure of the wing, so instead of making it aerodynamic, you're more concerned with can it withstand the aerodynamic forces without breaking. Or maybe you could work on the structure of the cabin. Those walls are actually thinner than you may think and need to be designed just right. And this is also a career you could see a mechanical or even a civil engineer doing because they learn a lot about structures in their curriculum. Overall, as an aeronautical engineer, you'll take a bunch of classes that cover the basics of everything. Some basic structures classes, propulsion, controls, and more. Then you can dive more into one of those if you get a master's. And there are more subfields I didn't talk about, like design, which is more about analyzing the aircraft as a whole and choosing the proper landing gear, what engine to use, the passenger cabin, and so on. More broad and less technical than some of the others. Or you could even have the option to take further materials science or engineering classes. I didn't mention this, but at supersonic speeds, the friction from the air molecules gets so intense that it can cause the aircraft to heat up to several hundred degrees Fahrenheit. A materials engineer may have to work on this and choose the materials that can handle those temperatures, but it's possible that an aerospace engineer could as well. And I'm going to end there. Remember, aeronautical engineering can encompass more than you may imagine when it comes to careers, so be sure to look into everything. If you like this video, don't forget to like and subscribe, and I'll see you all next time.